Okay, now we have our force vector as a function of position. And there is a perfectly good vector field. And since we know what a vector field is, we don't have to elaborate too much, okay? This is a vector field. Fairly easy to draw a picture of this vector field. We'll draw the source in here, the 2 microcoulombs. We don't need that 5 microcoulomb charge at any point, but if we put it at any point, we know what the force is going to be, right? Okay, so if I do this at, let's say, this radius, and then at double this radius, or distance circle, on a circle of 1 radius, then double the radius, the force is going to be a force of repulsion, and I can sketch that. Like so, at every point around this circle. It's going to be a force directly away, force in the direction of xi plus yj, and we know where that is. It's directly away from the origin, okay? And if I double the distance, the force becomes 1/4 as great. So I draw vectors, making a half-hearted attempt to make them 1/4 as great. So we can visualize what this field looks like. If I come in closer, the vectors are going to get 4 times as long. If I come in twice as close, vectors are going to obliterate both of these two if I try to draw them in the same direction, right? So I could draw a set of vectors, because of course you have the same vectors all the way around here at every point, but you just don't have time to draw all infinitely many of them, right? So I could draw vectors here that are 4 times as long as this one. That's not 4 times, gotta go a little further, okay. So 4, 1, 2, that's only about 3, but we'll go with that. So I could draw the field something like this. And I actually should have drawn the vectors a little longer. Whoops, I drew that one a little longer, okay? And I could have been more careful, but you get the idea how this field behaves as an inverse square field, just by looking at distances that are twice as great or half as great, okay? So we get the picture. The other thing is, this is a conservative field. And if you know multivariable calculus, and you guys do, test this. Path independent, derivable as the gradient of a potential function, right? Of a potential energy function, actually, in this case. The electric field that's the force per unit of traveling charge. And we usually call this test charge. but I didn't want to confuse things with the conceptual idea of a test charge. We'll talk about that next time, okay? This is what you would get if you put this is what you get if you put 5 microcoulomb charges at these points, right? This is going to be independent of that 5 microcoulomb charge, okay? And then if you multiply this by, let's say, what you get here by 10 microcoulombs, you're going to get twice as much force, okay? So it's going to be proportional to the number of coulombs that you put at a point, and it's going to be independent of how many coulombs we actually use. And I'm not sure I said that very well, but the field is going to look very much the same as this one. And I can draw field lines all the way around, right? Not field lines, but vectors. And of course, we'll have field lines that follow the vectors, and the field lines are just going to be lines through the origin, right? And all the vectors will be parallel to the field lines. So, we can say F equals QE is a force on charge Q within the field. Okay? Well, that takes care of the first 3 chapters on electricity. Really does. But you probably need to look at some details and work out the details. But there's your scheme. Oh yeah, the other thing is that there's your curve C. The potential energy change from A to B for the 5 microcoulomb charge, because this is very specific to that charge and the 2 charges that we have, is just the integral of F dot ds over whatever curve you want to use from here to here. Okay? And if I was going to use a curve from here to here and actually integrate over it, and we've done this in multivariable calculus, and apologies to anybody who might be watching this who didn't have multivariable calculus. Yeah. I'd integrate over a circle here, over which the field is perpendicular to the curve and gives you 0 dot product with your delta S vector. Okay? And then from here to here, and you end up with an integral just much like the one we just did, because the force then only depends on R, and it's always in the direction parallel to the path. Okay? So your F dot ds just becomes very simple function of R, which is why I kept writing R's, because that's what I'm used to. And by analogy, and then I'll let you go because it's time and past time. But if I wanted to do the integral from here to here, same point A to B, here, or the more sensible path here, and they're the same because of the conservative nature of the field, path independent. Okay. The integral over the same curve of E dot ds is And I said potential change. Okay, now it's potential change. Okay? But, and I might have turned out the sign right there. I have to stop and think through that. But, okay, something about that seems wrong, but I have to think it through. And I'm in a hurry to get rid of you guys, so I'm going to move here. Okay, so if you multiply the potential change, that's going to be in voltage. And you want to think about why. We'll bring the rest of this up next time, but I want you to work through as much of the rest of these questions as possible. With the numbers that I gave, I'm actually not going to change this.
Okay.
I just did it with everything reversed.
Right.
Okay?
So we need
You can do it and compare.
Okay.
A lot of the results will come out exactly the same,
Right.
but some of them are going to be different. You can think about why.